All right, so there's we've just finished some field work a little bit north of here last week, and to my embarrassment, I wasn't even aware of this conference. But since we fly a robot around the reefs, I knocked on Professor Eric Feron's door, and he said, "We've got a conference. Please come and talk. We can only fit you in at the end of lunch." My apologies, because we're interrupting your lunch. In a few minutes, this presentation should be online and we'll move to the PowerPoint. But I can start a little bit. I'm a marine biologist, and that pretty much means that I know very, very little about robotics, except for many years I had an idea in my head of the type of machine that I would like to see take over many of the tasks that I do as a marine biologist. And about 5 years ago, I began to build that machine. And what you see today is a combination of a lovely saying that Professor Feron said yesterday: the role of a control systems engineer is to sort out the mess made by the design engineers. Or in my case, solve all of the design imperfections that a marine biologist might make when he tries to build a robot. Okay, so we good? Yeah. I'll introduce you to Josh in a few minutes, but we'll start now. Okay. So, oh, okay. Top. A top for the advanced button? No. Okay, hang on. All right, so that was the first slide? Yep. All right. So we have a little company. It is literally everybody you see here, David, Josh, and myself. And we have built this underwater robot, which I want to make this a little bit of a fun presentation. It's been a journey, and like many robotics projects, I think there's many adventures along the way. I want to very quickly take you through that. The nice stuff is at the end, when we can show you some of the footage that we've collected and in the last week or so, and back in Australia, the Barrier Reef, etc., seagrass beds in Moreton Bay, and show you how that goes. So, I've got to do that one. All right, okay. So I said earlier, I've got a long career of much time underwater, measuring stuff, monitoring stuff, towing instruments around. I have used many of these machines, and I've done an awful lot of this. Hours and hours, maybe days and days of this. It's fun, don't get me wrong. I love it, but it's not a great way to record data. Fortunately, I happen to have a boat that allows me to go fast and go out to the sea and test my robot. Fortunately, I happen to be a pilot for full-size gliders. And I also happen to think that a lot of the design that we do underwater, until we can do as good as nature, we should probably copy it. So if you look at our machine, you would actually recognize the body shape of the trevally in the image. But I also was making airplane toys for my grandchildren, and the design of this particular yellow one caught my eye. So that's all kind of irrelevant, but here's the very first prototype that we had. It was really just to prove this notion that we could fly like a remote control airplane underwater, fast and controllable. And that was, for me, that was everything: fast and agile. Now, I'll introduce you to Josh, who will take over the talk in just a second, but Josh's background is mechatronics, and he's genius in that, and he's kept me on the rails as I build things. And he'll tell you more about his background and his contributions to the project after that. But we eventually got to the point where this machine was flying underwater. Our initial tests were just about fast flight, and we literally used radio frequency conducted up of an antenna to do control using RC controller, Metexis kind of flight control unit, etc. And it enabled us to get close to the seabed fast and keep some control. You'll see there had to be a few adaptations, such as a movable tow point so that it would deal with the different attitudes of the machine as it was flying. We eventually moved to our own, quite heavily modified electronics. You'll see that we had to overcome a number of challenges. We always wanted to go for the small form factor. This is our 3-inch pod. We 3D printed, but we found that that was just too weak. So we've got carbon sheathed 3D printed parts for sturdy wings and the like. And then we moved on to, here we go. So it proved to be very, very useful and allowed us to fly, for example, at 2.5, 3 meters per second down low. This is only this far above the seabed in water that is maybe 1.5, 2 meters visibility. And we fly this machine up to 12 or 15 kilometers per hour. We have never explored its top speed. My design criteria was, if it's fast enough that a human can see the images, we're not going fast enough. We're going fast enough when the computer can't keep up with the images. And that's why we want to use AI in our workflow stream, because it's the only way of covering vast areas very quickly. We've also had some detours in our design process. We wanted to change the nose of the machine to get the camera angle down so that we can make better use of a wide angle lens and for obstacle detection, as well as seeing detail on the seabed. That was never intended to sample the seabed, but it did several times. And in particular, at speed, it developed quite a wobble because of the turbulence coming off of the down pointing nose. But that's okay. You'll see my face is a lot happier there when we made the 4-inch pod with a different orientation on it. Josh would tell you that this picture shows me being lazy while he's working all night. What you don't know is that just in front of Josh is the turtle nesting beach, a beautiful tropical island, and he's there soldering all night. So there's a field robotics project in development. But the imagery that we collected is great, nice imagery. Who saw the shark? Right there. So this is imagery collected from the machine in the reef at speeds of, on that particular trip, we averaged around about 9.5 to 10 kilometers per hour at an altitude of around about 2 to 2.5 meters above the seabed. Anyway, I'm going to hand over to Josh now, because at about this point in time, we started developing our own, when I say we, I mean Josh, started developing our own electronics, and the project has come ahead from there.
Yeah, so just a bit of an overview of how the entire architecture works. We have the glider, which sits underwater, and it has relatively simple electronics inside it. That's a beagle bone, and its job is mainly to just sample all the sensors, send them back up the fiber optic cable. We're using all fairly low-cost sensors from Blue Robotics, and probably 50% of the parts cost of the entire glider is the camera on the right-hand side. So it's a pretty nice machine vision camera. And yeah, we have some custom PCBs inside to make the design super compact. I think it's only 200 millimeters long and 4 inches diameter, the pod.
Can I just say too, the entire machine is 780 millimeters wingspan and weighs approximately 6 kilograms, and is just put into a overhead luggage bag.
Oh, yeah. Yeah, so it's also not pictured here, but we have a Surface Compute box. It's about this big, just has an Intel processor in it, basically for running the web server at the top so that operators can use it. It's controlled by an Xbox controller over Bluetooth, which is, yeah, very nice and intuitive. And yeah, all runs on self-contained batteries, so there's no need to plug it into anything on the boat. It's and you can also tow it with your hand if you really needed to. There's only about in normal operation about 4 or 5 kilos of tension on the line when you tow it. But yeah, Brett.
Yeah, so can you interrupt? You mind?
Yeah, of course, please.
So how do you not bump into the bottom? How do you take control? You're going to come back?
Yeah, so maybe I'll skip forward a few to give some perspective.
Yeah.
Skip that. Yeah, so It has full actively controlled flight planes. So it has an IMU inside it, which is closing the loop to keep the depth at a constant depth. In this situation, because the seabed is so nice and flat, we actually close the loop around the altimeter as well. So that's fully automated control right now. There's someone mantelboarding behind it, and I think that's the pilot actually, and that's just someone driving the boat. So yeah, from control system point of view, it's extremely simple, and because of the design, it almost flies itself without any control. In refill environments, though, we have a flight feed, which looks a little bit like this. So the pilot can see what the glider is doing approximately on the top left icon. And you see a visual representation of what's going on. So using the Xbox controller, you can actively control it around extremely complex environments.
So the person on top of the Xbox is saying, I want you to go up higher and down lower?
Yeah, right now we're manipulating depth set point and we're doing direct rudder control. Yeah.
And the GUI allows the person driving the boat to see where they need to be. They can see the orientation. Primary navigation of the boat is actually being done by the pilot saying, I want to be.
Yeah, and you can see the map view here. This is a test of the camera focus. We actually didn't have a great screenshot, but when it's under operation, this boat and glider icon really show the relative positions of the two devices, so you can understand. It's configurable anywhere down from probably 5 meters to 100 meters. We've tried.
What were you doing on the thing? As a fiber optic cable, kind of front side.
Yeah.
We don't provide power to the glider. I was just wondering from a dynamics point of view, how long. Yeah, I know we run up, on the last week, we ran up to 100 meters.
Yeah.
So I want to get to the videos, but I just basically wanted to say there's a lot of pressure to go fully autonomous. And fully autonomous is great for some incredible things. But the reality is that with this configuration, we get the chance to review the data as we go. We literally saw things in the video that we stamped into it, called a diver to come to an exact GPS location, roll into the water and grab stuff that we can see on the seabed. So it's as a tool, as a rapid feedback, as we talk about adaptive sampling design. Travel up the reef and see something, you want to turn around, go back, you can do it here, but you can't necessarily do it in that time.
Position of
Yeah, that's one of our challenges. So we're kind of lucky with the tow cable that we can infer position. We say that with a 30-meter tow cable, we'll get about 5 meters accuracy or so. But it's all driven by parts costs. So the entire glider, similar to your machines, the camera is about $1,500 US, and the rest of the components are $1,500. So USBL, DVL, all those sensors are multiple times the entire part cost.
So just on this particular picture, I want to go back to something that Mike mentioned, Mike Gurman, in his talk this morning. He talked about the need for identification. Well, in fact, he talked about the need for genomics. So we're talking nanometers. But let's step up to his first visual scale, which was millimeters. So with millimeter precision, you can see most of the pole species, or at least some of them. But the need to survey it up to thousands of kilometers. So he's covering visual techniques covering 9 orders of magnitude. We don't do that, and we would never be as accurate as the stuff done by a diver close by like this. But we can also do 120 kilometers in a day. And if we have 10 meters of effective underwater visibility, we effective in a day.
No machine available that will do that.
No machine that can do it. So look, and so we packed the gear up and came to the Red Sea. That wasn't my boat, I'm all the way to the Red Sea. But here we go, a near vertical reef wall. You can see the glider. In this particular case, it's flying in a normal orientation mode. It's as in wings horizontal, camera facing down. But in the next segment, that we're actually flying it rotated so that the camera is facing back into the reef face, which is what we do when we particularly want photographic. And so we, in this particular instance, we were traveling at about 7 kilometers an hour, but a few minutes later, we were operating at 12 kilometers an hour in this terrain.
Yeah, and this is the depth is held by all the control loops, and the pilot is steering it left to right. There's no reason that we can't implement controllers to do that as well, but it's
So this is the 3D photogrammetry product taken from the first of the glider passes. And yep, I'm happy to confess it's not as precise as the stuff that was captured by the Sandy method guidance. But in terms of an unprocessed image, so there's no image control done on any of this, but we were producing a very, very reasonable 3D map of the area at the rate of what was that? That was about so it's a very, very fast survey method.
So this is
Yeah, this is from the that image was captured from the same flight as in this GoPro video.
I also want to show you another capability of the flight body. Is this one. The machine, the glider has a body that allows it to travel off track from the boat's train. So here you can see the machine is well out to the left port side of the boat, and it's following the edge of that reef. And you can see that more particularly in a minute as we come around to the second bombing. The glider will quickly.
Can you orientate the camera?
Yeah, the camera is 45 degrees now. Even though the glider's level, the camera is.
So you can see the fish following around the edge of the reef. So that allows two things. The design for that was based on working on the oceanic side of the reefs. And so this way the boat can sit outside of the surf rate, going up underneath the surf and survey the shallow, dangerous water. But it served its purpose here. There were several different use case applications that we built over the last week. The other element that we don't have footage here from, and we haven't pulled the footage from cans, because the body of the glider allows off-track movement, we can run multiple machines behind the one boat. And so in the last week, we were able to demonstrate 2 machines working from the one surface computer, so that they effectively double the swap width. Also allow us to do things like in these big, deep slope areas, 5 meters, 10 meters, 15 meters, able to cover the entire spot at one time. Sorry, I'm almost finished talking now. In fact, it's that's loud. I hope I was talking loud enough for you.
It was good for us in the front.
Oh, yeah. But look, we're here for the whole week, and we're certainly at the conference for the next couple of days. And you know, one of the reasons I looked up Professor Feron was I read in his interests that he was interested in in aviation acrobatic flight, and this is an underwater ROV which flies like an aeroplane, and some of our design challenges are about acrobatic flight, formation flying between multiple agents, and you know, the notion that, I mean, these machines, we have actually run them directly on their side so that they can photograph against a vertical wall or rotate them, etc. So there's a bunch of cool things we can do with them. And I look forward to perhaps we're going to catch up in the next day or two about some maybe some student projects, maybe some other work. We'll see how it goes. Look, hang on, was there one more slide at the tail end?
No.
Okay. Eventually this machine will be commercially available, and I hope that you don't see the same deltas between equipment component costs and sales price that many people do charge. But the reality is at this point in time, it's not ready for commercial use. So for the next year or so, we'll be offering it as a service. Our guys, it takes a bit of training. And in fact, the job description, if you want to fly the glider, the job description is you've got to understand boats. You've got to be able to drive them. You've got to be able to dive and tell me what's under the water. You've got to understand the geomorphology of a reef. And you've got to be able to not just fly a high performance airplane, but you actually have to be able to do formation flying. And if you can do all those things, you've got to roll in our team. Otherwise, we're just crashing gliders. There you go. But look, we train people, but it takes a little while. All right, okay. We train people, but it does take a little while. But the distances we can cover, the data sets we can get. For example, each one of these machines at 15 frames per second, 5 megapixels per image, is collecting in a full day almost 500,000 images. The data set is enormous. The machine learning applications based on this data set are enormous. We've only just begun to touch the surface. I actually see enormous opportunity for collaborations here with those in the sciences space, in the information processing, computer vision space, in the engineering space, in the control system space, etc. So pull us by the ear and let's strike up some conversations. And thank you for fitting us in.
My pleasure. Thank you.